22, we've got this situation when a dry cell is connected to a circuit with a load resistor of 4 ohm. There is a terminal voltage of 1.3 volts. When the load resistor is changed to 12 ohm, the terminal voltage is found to be 1.45 volts. Calculate the EMF of the cell and the internal resistance of the cell. Now I've drawn up the situation here for this. We've got the formula here for EMF, and remember the EMF is the total energy that a cell can deliver. Now what we have here is that when you have a current flowing, when it goes through this resistor here, and I call it R1, the 4 ohm, there is a 1.3 volt potential difference. Now what also happens here is as it goes through the cell, there's also this small r over here, and there's going to be a loss of energy, and I'm going to write it as V is equal to I times small r. That's actually going to be taken away from the EMF. So the EMF is the total energy, and it's actually equal to this 1.3 plus this V I times small r. Now, because we can take in the situation that both of these have got the same EMF here, the EMF of this cell and the EMF of that, and we also think we are assuming that our internal resistance is the same, we can set up two equations. Now, in looking at this equation, I can just expand this equation to be I R plus R, and IR over there when I expand that bracket. Now I can actually work out the current in each of these circuits, so let's just do that. For I1, from this formula over here, it's going to equal the V divided by R, which is 1.3 divided by 4, and for that I get 0.325 amps. And my I2 here would be the same thing, but here I've got 1.45 volts divided by 12 ohm, and I get for that 0.121 amp. Now I can therefore have two equations here. That my EMF is equal to IR. Now that IR will actually be obviously the 1.3 volt, because V is equal to I times R. So that's 1.3 plus the 0.325 times by the small r, which is my internal resistance. So we have one equation there. Second equation using this circuit over here. Here we've got 1.45 volts plus I, which is 0.121 times R. And because both of these are equal to my EMF, I can make them equivalent. So I'm going to get 1.3 plus 0.325 R is equal to 1.45 plus 0.121 R. I can solve for R. I can bring this over and subtract, and I am going to get 0.204 R, and I'm going to take this 1.3 over to the other side, and I'm going to get 0.15, and when I divide that out, the 0.15 divided by the 0.204, I get my R is equal to 0.74 ohm. Once I've got that, I can use either one of these two equations to solve for my EMF. So I can actually, let me just not do that. Let me go back to here. Let's just do this over here. So I'm going to get my EMF is equal to 1.3 plus 0.325 times 0.74. and I can just multiply that out and solve. So it's going to be 1.3 plus 0.325 times 0.74, and I get a answer here of my EMF is equal to 1.54 volts. So what that means is that the EMF, that's the total energy that it can supply, but what actually happens is that some of the energy is lost to the internal resistance, so it can only supply less to the external circuit. In this case over here, notice that because your current is less, your IR here is going to be less, and therefore you can supply more to your external circuit. That's why that's 1.45 and that's 1.3. More energy can be supplied to your external circuit.